We have a process, a monatomic ideal gas, which is initially at pressure P initial, volume V initial, temperature T initial. The final pressure of the gas is P initial over 2, so this is P. The final pressure is P over 2. The final volume of the gas is 2V. Initial volume is V. And therefore, what is the final temperature of the gas? Because P initial, V initial is nRT initial. This is an ideal gas, a monatomic ideal gas. Then I can have P final. So PV is equal to nRT initial. P final is P over 2. V final is 2V. It's again PV and RT initial. So I find that the final temperature is also equal to the initial temperature. What is the entropy change for this monatomic ideal gas? Well, since in this process you have no temperature change, you can think of an isothermal process in order to calculate the entropy change. So let's think about an isothermal process, reversible expansion. You can see its V is becoming 2V, and therefore the temperature change is 0, so the internal energy change is 0, and you have dq plus dw is 0. The heat that you're adding to the system, dq reversible, is minus dw. It is p dv. So the entropy change in the process, delta S, from initial to final, dq reversible over t, it's from initial state to final state, p dv over t. The temperature is constant, 1 over t, initial to final, nr T over V dV. The T's cancel. The entropy change is going to be nR natural logarithm V final over V initial, and I have V final is 2V, V initial is V, so it will be number of moles times universal gas constant times natural logarithm 2. So let me keep this answer here, nR natural logarithm 2. Now I want to solve this problem with a different reversible process. Okay, so let's have an alternative approach here. Alternatively, what I'm going to do is, first I will go from PVT to P2V T over 2. Sorry, if you go from PVT to P2V, you will be going to 2T because PV is equal to nRT. And then I will go from in two steps. Step 1. In step 2, I will go from P2V 2T to P over 2 2V back to temperature T. So this is my initial state. This is my final state. I'm doing it in two steps. All right. So the first process is isobaric process. What is the heat added in an isobaric process? dq is equal to n Cp dt. Since this is an ideal monatomic gas, Cp I will take to be 5 over 2 R. That's neglecting vibrations. Oh, sorry. Yes, Cp is 5 over 2R because I only have translations for a monatomic gas, and Cv is 3 over 2R. Only translations. All right. So therefore the heat that I'm adding here is 5 over 2R N dt. So the entropy change in the first step will be integral from the initial temperature T to final temperature 2T, 5 over 2 nR dt over T. This is from initial to final state, dq reversible over T. So in the first process, I have 5 over 2 nR natural logarithm 2t over t, which is 5 over 2 nR natural logarithm 2. Now I go to the second process, which is isovolumetric. In the isovolumetric process, I have dq is equal to n cv dt, and this time I will have a change in entropy in the second step. I'm going from a temperature 2T to T. Cv is 3 over 2R, 3 over 2 and R dt over T. So I will find that the entropy change in the second process is 3 over 2 and R natural logarithm 1 over 2. All right, so let me open up some space here to conclude my discussion. So the total entropy change in the alternative method is delta S1 plus delta S2. It will be equal to 5 over 2 nR natural logarithm 2, and natural logarithm of 1 over 2 is minus natural logarithm of 2, so minus 3 over 2 nR natural logarithm of 2. So my answer is nR natural logarithm of 2. So the answer that I'm getting using the alternative method of two reversible processes that will take me from the initial to final state, isobaric and isovolumetric processes, give me exactly the same result as the isothermal process. So first method, I had isothermal reversible expansion. In the second method, I had an isobaric process first and an isovolumetric process following this to take me from the same set of initial conditions to the final conditions. Because entropy is a state variable, it doesn't depend on how we go from initial to final conditions. The result will be